This is SpaceTime, Series 22, Episode 42. Coming up on SpaceTime, 100 years of gravity, a new general relativity clocks experiment, and discovery of one of the oldest known globular clusters. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
It was 100 years ago this month that observations performed during a total solar eclipse by Author Eddington proved for the first time that light can be physically bent by gravity. The gravitational bending of light was first predicted just over a decade earlier by Albert Einstein in his famous 1916 theory of general relativity. But for many in British science, Einstein's general relativity theory was tantamount to heresy, as it challenged the great British scientist Isaac Newton's famous 1680s theory of universal gravitation. Amplifying this problem was the thunderous roar of cannons of the Great War blazing across Europe, making Einstein's so-called German science most unwelcome in Mother England. Of course, what made this attitude even worse was not just the fact that Einstein was right, because he was, but also the fact that he was a pacifist who hated war and an internationalist who firmly believed that the peoples of the world should unite across national, political, cultural, racial and class boundaries in order to advance all humanity. Einstein's general relativity, and as a result science's understanding of the universe, had become trapped by wartime blockades and vicious nationalism. Enter the British astronomer Author Eddington, who read Einstein's paper and understood the theory's complicated mathematics. Eddington championed Einstein's general relativity theory, writing numerous books and carrying out lectures on the science behind it, working hard to convince researchers of its truth. And it was a noble cause. Einstein the Jew and Eddington the Quaker both believed science should transcend the fractious divisions caused by war and prejudice. One of the big problems with relativity theory is there are many fascinating but difficult aspects to accept, such as twins aging at different rates due to time dilation related to mass and speed. Another was the gravitational bending of light. However, this one could easily be tested, simply by photographing and mapping the exact position of background stars, and then seeing if their locations appear to change as their light was being bent by the gravitational effect of the sun as it passed near the path of their starlight. Of course, there's one big problem with this, and that's the sun's glare. The brightness would mean observing any apparent positional change would be impossible. But luckily, the heavens were about to provide a solution. That was to come by way of the May 1919 total solar eclipse. Einstein's general relativity predicted that light from a star would be bent by 1.7 arc seconds, or about 1/60th of a millimeter. So 2 expeditions were organized to see if Einstein's science was right. One went to Brazil, and the other, just in case Brazil was overcast, was led by Eddington in West Africa. Then on the 29th of May 1919, 100 years ago, astronomers watched as the skies darkened and the eclipse unfolded. For 6 minutes, as overcast skies threatened, scientists watched, took images and measured the starlight to see if it was really being displaced by the sun's gravity. Then, after months of intense measurements and calculations, Eddington and consequently Einstein had their proof. The position of the star appeared to change in the sky as the sun's gravity bent the light coming from it. The announcement was hailed as one of the highest achievements in human thought by the Royal Society, while the Times called it a revolution in science. Almost overnight, Einstein was thrust from a relatively obscure academic to become the most famous scientist the world had ever known. However, Einstein wasn't there for the announcement. He was gravely ill from wartime starvation, barely able to raise himself from his sickbed. It was thanks to Eddington that Einstein's theory of general relativity had been proven correct, and consequently, science's view of the universe would never be the same again. The European Space Agency's Director of Science, Gunther Hassinger, says Eddington's historic measurements inaugurated a century of exciting experiments, investigating gravity on Earth and in space, and proving general relativity in ever greater detail.
Discovery of the gravitational light bending of the stars around the sun in 1919 were really embedded in a very exciting history, and that history connected to Einstein's theory of relativity is also very closely connected to the First World War. There was an astronomer in Potsdam His name is Erwin Finley-Freundlich, and he was obsessed about trying to prove Einstein's theory of relativity. He was working very closely with Einstein, and already in 1914 he set out to go to observe an eclipse in the Crimea. But that was at the evening of the First World War, and so he was immediately captured and locked away and was not able to do the observations. And in a sense, this was a blessing in disguise, because at that time Einstein's theory of relativity was not yet completely ready, and he still was missing a factor of 2. So his predictions were a factor of 2 off from the real result. 2 years later, 1916, Karl Schwarzschild was actually the first one to solve Einstein's equations very simply. And he did this on the front, in the Russian front, while he was a soldier in the First World War. And Einstein then later basically presented his results in Berlin and said he would never have thought that his equations would have such a simple solution. Now, unfortunately, Karl Schwarzschild died a year later from a disease that he has actually caught at the front. And so we were missing a big genius in astronomy for the rest of the time. But his equations are still what we are basing our current understanding of black holes on. And then Sir Arthur Eddington, at that time he was not yet Sir, he was working at Cambridge. He was a professor at Cambridge at that time. And during the First World War, there was almost no communication between Germany, Einstein, and Cambridge. But Eddington had a private version of the Einstein's theory of relativity. And he used that theory in order to evade becoming a soldier in the First World War, because he convinced the London military that he doesn't have to go to war, but he is preparing a solar eclipse. And so Eddington, right after the First World War, then set out to West Africa. And there was another expedition to Brazil where they observed the light bending, and they exactly measured, or roughly measured, what Einstein had predicted. And I think the most important effect of this measurement was that Einstein all of a sudden became famous like a rock star. And from then on, everybody knew the theory of relativity, and a lot of people were trying to measure it, to prove it. And in the years after, there were many, many different and more accurate measurements that proved the theory of general relativity. 100 years later, gravitational waves were discovered, which was a major prediction of the theory. And then also just last year, the gravitational redshift from the black hole in the galactic center was detected with telescopes at ESO. And so I think this rounds up the 100-year history of the general theory of relativity. When you think about similar events that could happen now or in the future, I cannot help but think about the mess which we are in, our ignorance about dark matter, dark energy, black holes. We don't have a clue yet about what dark matter is, what dark energy is. We know something about black holes. But somehow I have the feeling that we are in a similar situation than 100 years ago, that there has to be something, a new Einstein to come to explain to us how all of that fits together. For me, it's highly speculative, but also highly fascinating to think about whether black holes have something to do with dark matter. And I think we are set up for the next decades to really do fundamental observations in this field.
That's Gunter Hasinger, the European Space Agency's Director of Science. And this is Space Time. I'm Stuart Gary. Now, while we're on the subject of general relativity, next year the International Space Station is expected to play host to the most precise clocks to ever leave the Earth. Accurate to a second in 300 million years, these clocks will push the measurement of time to test the limits of the theory of general relativity, and consequently science's understanding of gravity. As well as predicting the bending of light by mass, as discussed earlier in the show, Einstein's general relativity theory also predicted that gravity and speed influences time. The faster you travel, the more time slows down, but also the more gravity's pulling on you, the more time slows down. In other words, technically, your feet are slightly younger than your head. 40 years after Eddington confirmed the bending of light around the sun, the Pound-Remke experiment first measured the redshift effect induced by gravity in a laboratory. But a century later, scientists are still searching for the limits of this theory. And that's where the European Space Agency's Atomic Clock Ensemble in Space, or ACES project, comes in. ACE's lead scientist Luigi Cassiaputti says the theory of relativity describes the universe on the larger scales. But on the border with the infinitesimally small scale, the theory doesn't jive and remains inconsistent with quantum mechanics. Today's attempts at unifying general relativity with quantum mechanics predict violations of Einstein's equivalence principle. This principle details how gravity interferes with space and time, and one of its most interesting manifestations is time dilation due to gravity. It's an effect which has already been proven by comparing clocks at different altitudes, such as on mountains and in valleys, and of course in space. Clocks at higher altitudes show that time is passing faster with respect to a clock on Earth's surface. That's because there's less gravity from Earth the further away you are from the planet. Flying at 400 kilometers in altitude aboard the International Space Station, the atomic clock ensemble in space will be able to make more precise measurements than ever before. ACES will create an internet of clocks, connecting the most accurate atomic timepieces the world over and comparing their timekeeping with ones on the orbiting outpost. Comparing time down to a stability of hundreds of femtoseconds, that's a millionth of a second, requires techniques that will push the very limits of current technology. ACES has two ways for clocks to transmit their data. There'll be a microwave link and an optical laser link. Both connections will exchange two-way timing signals between ground stations and the space station. And the unprecedented accuracy the setup offers will also bring some nice bonuses for the ACES experiment. Atomic clocks on the ground can be compared amongst themselves, providing local measurements of geopotential differences, thereby helping scientists to better study the Earth and its gravity. And the frequencies of the laser and microwave links will help scientists better understand how light and radio waves propagate through the troposphere and ionosphere, thus providing new information on climate. Finally, this Internet of Clocks will allow scientists to distribute time and synchronize their clocks worldwide for large-scale Earth-based experiments and for other applications that require exquisitely precise timing. In fact, the next generation of atomic clocks and the link techniques being developed could one day even be used to observe gravitational waves. Importantly, if ACES does find tiny violations in general relativity, it may well be opening a window on a new theory of physics. You're listening to Space Time. I'm Stuart Gary. Astronomers have discovered one of the universe's oldest known globular star clusters, dating back some 12.8 billion years. The stunning image, reported in the monthly notices of the Royal Astronomical Society, looks back into the early history of the cosmos and sheds new light into how our galaxy formed. Globular clusters are tight, gravitationally bound spherical bundles containing thousands to millions of stars, which were all originally formed at the same time in the same molecular gas and dust cloud. Researchers zoomed in on a globular cluster called HP1, located in the central bulge of the Milky Way galaxy. The discovery was made using the high-resolution adaptive optics imaging capabilities of the Gemini South Observatory in Chile, together with data from NASA's Hubble Space Telescope. Adaptive optics are a wonderful tool. You see, stars twinkle because of the turbulence and temperature variations in different layers of Earth's atmosphere. It's a lot like lying at the bottom of a pool and looking up at the sky through the water column. Twinkling stars might be great for romance, but they're not very good for astronomy, and that's why scientists place their optical telescopes on high mountaintops in order to get above as much of the atmosphere as possible. But for really the best images, even the tallest mountains aren't enough. So one solution involves putting the telescope in space, such as the Hubble Space Telescope. The thing is, that's really expensive, and you're limited by the size of the rocket able to carry the telescope up there. And that's where another solution called adaptive optics comes in. Adaptive optics uses lasers beaming up through the atmosphere to detect turbulence in different layers of the air, and then rapidly adjust the shape of the telescope's primary mirror to compensate for this turbulence, dramatically sharpening the image. The Gemini South Telescope's ultra-sharp adaptive optics images allowed astronomers to determine the ages of stars in the cluster, confirming that they're some of the oldest stars in the galaxy, dating back to a time when the universe was less than 1 billion years old. And that makes HP1 one of the surviving members of the fundamental building blocks that assembled our galaxy's inner bulge. Until a few years ago, astronomers believed that the oldest globular clusters were only located in the outer parts and halos of galaxies, while it was only younger star clusters that resided in the innermost galaxy regions. However, new research suggests that ancient star clusters can also be found within the galactic bulge and relatively close to the galactic center. Globular clusters are great because they can tell us a lot about the formation and evolution of the Milky Way. While most globular clusters are thought to have coalesced out of the primordial gas and dust which collapsed to form the spiral disk of our Milky Way galaxy, others appear to be remnant cores of other dwarf galaxies, shredded by the gravity of our own Milky Way as it cannibalized them. The Milky Way has roughly 160 globular clusters, and about a quarter of them are located within the greatly obscured and tightly packed central bulge region of the galaxy. The spherical mass of stars, some 10,000 light-years across, which forms the central hub of the Milky Way, is composed mostly of old stars, gas and dust. Among the clusters within the central bulge are those which are the most metal-poor, that is, lacking heavy elements. That includes HP1, having long been suspected as being one of the oldest. So, thanks to these new observations, we now know that HP1 is a fossil relic, and that means it serves as an excellent tracer for the Milky Way's early chemical evolution, helping scientists better understand how our galaxy formed. To determine the globular cluster's distance from Earth, astronomers used archival ground-based data to identify 11 RR Lyra variable stars inside HP1. RR Lyra variables are periodic variable stars, named after the prototype and brightest example, RR Lyra. They're all very ancient stars, created directly out of the remnants of the very first stars to have formed, and they're commonly found in globular clusters where they're used as what are called standard candles to measure nearby galactic distances. RR Lyras are aging, pulsating stars about half the mass of the Sun. They're thought to have shed a lot of their mass during their red giant phase, before which they would have been similar, though slightly less massive than the Sun. Using standard candles to measure cosmic distances involves knowing how bright a star is and comparing that to how faint it seems to determine how far away it is. It's a bit like looking at a row of streetlights down a road. You know they're all the same brightness, but the ones further away will appear dimmer than the ones nearer to you. In the case of RR Lyras, the relationship between their period of pulsation and their absolute brightness makes them good standard candles for relatively nearby targets, especially within the Milky Way. The pulsations in the stars are caused by the Kappa mechanism. You see, in a normal star, any increase in the compression of the atmosphere would cause a corresponding increase in the temperature and density, producing a decrease in the opacity of the atmosphere and allowing heat energy to escape more rapidly. The result is an equilibrium condition where temperature and pressure are always kept in balance. However, in special cases, the opacity increases with temperature and the atmosphere becomes unstable against pulsations. If a layer of the stellar atmosphere moves inwards, it becomes denser and more opaque, causing heat flow to be checked. In return, the heat increase causes a buildup in pressure that pushes the layer back out again. This process causes the layer to repeatedly move inwards and then back outwards again. It's known as stellar non-adiabatic pulsation, and it results from this Kappa mechanism, occurring in regions where hydrogen and helium are partly ionized, or where there are negative hydrogen ions. In the case of RR Lyra variable stars, it occurs where there's a partial secondary ionization of helium. Anyway, that's the background. The observed brightness of these RR Lyra stars indicates that the HP1 globular cluster is about 21,500 light-years away, placing it just 6,000 light-years from the galactic center and well within the galaxy's central bulge. The authors also used the Gemini data, as well as data from Hubble, the Very Large Telescope, and the Gaia mission, to refine the orbit of HP1 within the galaxy, showing it gets as close as around 400 light-years to the galactic center, less than a tenth of its current distance. You're listening to SpaceTime. I'm Stuart Gary. India has successfully launched a new spy satellite. The PSLV, or Polar Satellite Launch Vehicle, was flown from the Datish Dhawan Space Centre on the Bay of Bengal coastline in its QL configuration with 4 strap-on solid rocket boosters. The C-45 mission's primary payload was the 436-kilogram EMISAT Electronic Signals Intelligence Gathering Spy Satellite for India's Defence Research and Development Organisation. The new spacecraft will monitor the radio signals and other electronic activities of India's aggressive neighbours, Pakistan and China. It'll be perched in a 749-kilometre-high sun-synchronous polar orbit. Going along for the ride were some 28 smaller satellites and CubeSats. Included were 20 next-generation Flock 4A Dove Earth imaging satellites for San Francisco company Planet Labs. Also aboard were 4 Lima 2 satellites for another American company, Sapphire Global. The Lima 2s are designed to track the positions of shipping and aircraft through their automated identification systems, as well as monitor atmospheric conditions such as temperature, pressure and humidity. By the way, signals from GPS satellites are affected by the atmosphere they're passing through. Another satellite in the manifest was Switzerland's Astrocast-02, an L-band telecommunications 3-unit CubeSat. Then there's a 2-unit Spanish CubeSat, which will act as a prototype for a new constellation of ship and aircraft tracking satellites. And finally, there's the Lithuanian Nanoavionics M6P and Blue Walker 1 modular test satellites. They were released into a 500-kilometer high low Earth orbit to test new 3-axis control, communications and propulsion systems. Now, after deploying its 29 satellite payloads, the PSLV launch vehicle's PS4 upper stage began a new mission, deploying its own solar panels and remaining in orbit for a further 6 months, where it's hosting 3 additional payloads. These include another shipping and aircraft automated identification system receiver, as well as an amateur ham radio repeater and an analyzer for scientific ionospheric studies. The C-45 mission is the second flight this year and the 47th overall flight for the Indian Space Research Organisation's PSLV rocket. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. Spacetime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more Spacetime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.